If you have a proportional only controller, before we get started with chapter 11, let's take a look at how different types of controllers lead to certain types of responses in closed loop. If you only have a proportional controller, then as you increase the proportional gain, the offset decreases. You'll often see oscillations, and in some cases, the closed loop system may even become unstable. Now, if you have a proportional integral controller, then as you increase the integral time constant, because integral time constant corresponds to a decrease in the integral action, the process, the closed loop response, gets slower and slower with increasing integral time constant. On the other hand, with increasing proportional gain, the process gets faster and faster. Now let's move on to closed loop systems in chapter 11. There are two primary objectives for any given controller. Let's consider a simple heating tank example with a controller that is controlling the exit temperature in the tank by adjusting the steam flow rate into the heating coil of the tank. Naturally, when you design a controller, you expect the controller to take the process control variable, which in this case is T of T, to the set point as fast and as possible or as desired. So if you were to plot the set point or temperature versus time, then when there is a step change in the set point from an initial value of T1 to a final value of T2, there are many options for us in terms of how the process is taken from one set point to the other set point. You could design a controller that takes it slowly with no oscillations, or you could design a controller that exhibits some oscillations but takes the process from one set point to the other a bit faster. Or you can design an extremely fast controller that takes the process very rapidly to the final set point but shows large oscillations. Now you have to decide when you're designing a controller the type of response that you want from the controller. And often, as a control engineer, you have to make this decision, or you will make this decision based on the process on which this controller is going to be applied. So the process of taking the process from one set point to another set point is what is called servo control. Now let's consider a slightly different scenario where our objective is not to move the process from one set point to another, but instead it is to make sure that the process stays at its set point despite a disturbance in the inlet temperature Ti. If the inlet temperature increases, naturally you will notice that the exit temperature is also going to increase. However, if you design a good controller, that controller must bring the process back to its set point. Again, there are different ways in which your controller can bring the process back to the set point. That depends on what type of a response you desire or you require based on the process. This approach of bringing the process back to its set point in the presence of disturbances is what is called regulatory control. The behavior of the closed-loop system in following set points or in rejecting disturbances is something that is going to depend on how well the controller is tuned or how the controller is tuned. One obvious way to understand the closed-loop behavior of the controller and the process when they are together is to look at the transfer function between the output and the set point, and also the transfer function between the disturbances and the output. These two transfer functions would determine the type of response we're going to get in closed loop, whether it's servo control or regulatory control. So to understand how the controller interacts with the process and behaves in closed loop, we must study the behavior of the closed loop transfer function between the output and the set point, and the closed loop transfer function between the output and the disturbances. So in the rest of this chapter, we're going to learn how to derive the closed loop transfer function between the set point and the output, and also the disturbance and the output. And this transfer function, T over TSP, is what is called the closed loop transfer function. In fact, the transfer function Y over D is also called the closed loop transfer function. There are multiple closed loop transfer functions that one can derive. T over TSP is one of those transfer functions. And in this chapter, our goal is to represent controllers, processors, sensors, and the rest of the components of a closed-loop diagram using block diagrams and then derive closed-loop transfer functions. So let's start with the block diagram representation of the process first. We'll go back to the blending tank example that we've used several times in this course. The control variable in this example is the exit concentration, and the manipulated variable is the flow rate of pure A into the tank. So let's try to represent each component of the control loop using a transfer function. And start with the process, which of course is the most important component of the closed loop system. The approximate dynamic model of this process was already derived in chapter 2, and it's given by the sum of two transfer functions, one transfer function between x1 and x, the other transfer function between w2 and x. Remember that we should always have the dependent variables on the left-hand side and the independent variables on the right-hand side. So in this case, if you're asked to find the transfer function between x1, a disturbance variable, which is also an independent variable, and x, that transfer function is k1 over tau s plus 1. On the other hand, if you're interested in the transfer function between w1 and x, that transfer function is k2 over tau s plus 1. Of course, we can represent this using a block diagram where the first block has an input x1 and the second block has the input w2. The outputs of these two blocks are added together to generate the eventual concentration in the exit stream x. xd represents the effect of x1 on x, and xu represents the effect of w2 on x. Similarly, one can derive a transfer function for a composition sensor-transmitter combination. It turns out that sensors and transmitters also have certain internal dynamics, and therefore they can be represented using a transfer function. However, their dynamics are so fast compared to the process dynamics that their time constants are often extremely small. If the time constant of a process is of the order of minutes, the time constant of a sensor or transmitter could be as small as a fraction of a second. In this course, we're going to assume that the transfer function of a sensor-transmitter combination is km over tau m s plus 1, where tau m is an extremely small time constant compared to the process time constant. xm is the actual measurement in electrical signals. It's an electrical signal, typically in the range 4 to 20 milliamps. And x is the true concentration. So a sensor does not directly give you the true concentration as a measurement. Instead, it's going to generate an electrical signal, and we are trying to find the transfer function between the raw value of the concentration and that electrical signal.
Okay, let's get started with block diagram representation of various components in a closed loop control system. It turns out that in control theory and in process control in general, we represent each and every component that we are interested in using a block diagram. So it's very important to represent these components in a block diagram so that we can in turn use these block diagrams to derive closed loop transfer functions. We've already looked at the block diagram of the process in the previous lecture, so let's consider sensor and transmitter block diagram. When it comes to sensors and transmitters, they often exhibit extremely fast dynamics, and therefore these dynamics can be approximated by a first order transfer function with a small time constant, or in some cases even a simple constant with no first order transfer function. On the left hand side, I have xm, which is the electrical signal from the sensor, over x, which is the actual raw measurement from the process. And their transfer function is km over tau m s plus 1, where tau m is in general extremely small compared to the time constant of the process. And the reason for doing this sort of an approximation is as follows. If you look at the figure on the right hand side, I have plotted xm and xt versus time. You'll notice that when there is a change in the concentration, let's suppose that it's a step change, the change in the electrical signal is not going to be exactly a step change that represents the change in the concentration. Instead, it's going to have, the sensor itself is going to exhibit some inherent dynamics, and therefore the change in the electrical signal is going to be fast, but it's not going to be exactly a step change. Now, as I mentioned earlier, typically we assume that the process time constant tau is much larger than the time constant of the sensor. In fact, if that were not the case, it makes no sense to use a sensor. And often this relation between the electrical signal out of a sensor and the concentration is represented or approximated using a simple constant Km. So using a block diagram, we can represent this as follows. The input is the raw concentration X. The output is the electrical signal Xm, the measured current. And those two are related by a first order transfer function. The next element in the closed loop is the controller itself. Let us suppose that we have a PI controller, and therefore its transfer function is going to be Kc times 1 plus 1 over tau is. Now a controller, unlike the other elements in the process, receives two signals. One is the set point, and the other is the signal from the sensor transmitter combination. Typically, the signal from the sensor is a 4 to 20 milliamp signal, and the controller also receives a set point, which is often passed through a converter so that the controller compares apples to apples. In other words, the controller has to compare electrical signal to electrical signals, because instead of receiving a value for the original concentration, the controller receives an equivalent electrical signal. The control error is now the difference between the set point in current and the measurement signal, also expressed in the current units, in the units of current. The converter transfer function is Km. Now the block diagram for a controller can be shown as follows. We take the raw value of the set point, convert it into an electrical equivalent signal, X delta SP, and that conversion is done using the block Km. The input to the controller is the difference between the electrical signals for the set point and the actual measurement, which is Xm. So let's continue with the derivation of block diagrams. The next component in the closed loop control system is current to pressure transducer. It's an instrument that converts the current signal from the controller into a pressure signal. And typically these transducers have extremely fast dynamics, in other words, negligible dynamics, and therefore they can be represented using a simple gain. The signal from the controller is P. It is typically a current signal in the range 4 to 20 milliamps. It's then passed on to an IP, current to pressure transducer, which converts it into a pressure signal in the range 3 to 15 psig, pounds per square inch gauge. Now this transfer function between PT, the pressure signal, and P, the electrical signal from the controller, is often treated to be a constant, KIP. In other words, when there is a change, a step change, let's say, in the current signal to this particular instrument, then you will notice an immediate rapid change in the pressure signal as well. In fact, the change in pressure signal is likely going to be very similar to the change in the electrical signal, with the difference being in the gains of these two signals. There are two different types of valves. There are valves where the pressure signal is applied on top of the diaphragm in the valve. These valves are called fail-open valves because in fail-open valves, the valve opens automatically when there is a failure in the pressure signal. On the other hand, there are also what are called fail-close valves, where the pressure signal is applied under the diaphragm used in the valves. And because of that, when there is a failure in the pressure signal, the valve closes automatically. Now this instrument can be represented using a block diagram where the input is the current from the controller, P, and the output is the pressure signal to the control valve, KIP. The only other element that's remaining for us to develop a transfer function is the control valve. The control valve is also often called the final control element. A first order transfer function is often used to represent the dynamics of a control valve. W2 is the flow rate from the control valve. PT is the pressure signal applied to the control valve. And the dynamics of these two variables are represented using the transfer function Kv over tau Vs plus 1. And the block diagram is similar to the other block diagrams. The input is Pt, output is W2. The transfer function is a first order transfer function. Now what we can do is put these different block diagrams together and create a closed loop block diagram. So that's the process and that's the disturbance. This is a block diagram we've derived a couple of lectures ago. Now we can take the control variable, the measurement of the concentration, send it to a sensor with the dynamics Km over tau m s plus 1 or simply Km if the time constant is extremely small. And this measurement is then subtracted from the set point that is converted into an electrical signal. X tilde SP is the electrical signal equivalent of the set point. The difference between the set point and the measured variable is the control error, which is then passed on to a controller. Now in this particular example, we've used a PI controller and therefore we're going to use the transfer function Kc times 1 plus 1 over tau Is for the controller. Now in the class, somebody asked me that if the gain Km used on the set point and the gain of the sensor Km are going to be the same. They have to be the same because the conversion factor must be the same. The only difference is that in the sensor, you could potentially have dynamics in the form of 1 over tau ms plus 1, whereas in the converter, which is often something written in a programming language, there are no dynamics. The controller is followed by the gain related to the current to pressure transducer, which is then followed by the valve dynamics Kv over tau Vs plus 1. Now when we put all these together, we get what is called a closed loop block diagram. This is a negative feedback closed loop block diagram because we are subtracting the measurement X from the set point XSB. Now what is the use of this closed loop block diagram? If you make a step change in the set point, you obviously cannot expect the same step change in the control variable. Instead, there is going to be a lag between the change in the set point and what you actually see or observe in the control variable. In some cases, depending on how the controller is tuned, you may see a slow, sluggish response with no oscillations, or if a controller is aggressively tuned, you may see oscillations and an aggressive response. The same is true with the disturbance variable. When there is a disturbance change, let's say a step change in the disturbance variable, you expect the controller to bring the control variable back to its set point, aggressively or slowly, depending on how the controller is tuned. Often in designing a controller, you specify a desired closed loop transfer function such as Kd over tau ds plus 1 and use that to back calculate the corresponding controller that gives the desired closed loop behavior. Now let's try to derive the closed loop transfer function so that we understand the effect of the set point and the disturbances on the control variable. Now here is a generic closed loop block diagram. So far we have derived a specific closed loop block diagram for the blending process. It turns out that a closed loop block diagram for any given process will have a similar structure, and here is that closed loop block diagram. And this is often called a negative feedback controller because you're subtracting the control variable from the set point. Now let's try to derive a transfer function between y and ysp for set point changes. This transfer function is often called complementary sensitivity transfer function. Now, in order to derive the transfer function between the set point and the control variable, we're going to assume that the disturbances are zero, and therefore y prime is equal to yd prime plus yu prime, which in turn is going to be equal to yu prime because yd prime is zero.
Now, this is a generic closed-loop block diagram that we have derived in the previous lecture. And this block diagram has the set point on the left-hand side and the control variable at the other end on the right-hand side. It has two external inputs. One is the set point YSP, the other is the disturbance D. And there is only one output, which is the control variable Y. Between the set point and the control variable, there are several other blocks corresponding to various elements in a typical closed-loop system. The set point has to be converted into an electrical signal using the constant Km. The control error between the set point and the control variable E of S is then processed by the controller GS, which is then the signal from the controller is processed by the IP transducer GIP, which is then processed by the valve GV, which in turn affects the process GP. GD is the disturbance transfer function, and GM is the transfer function of the sensor. This is a typical negative feedback controller. Now let's try to derive a transfer function for set point changes. In other words, a transfer function between the set point YSP and the control variable Y. Now Y is obtained by adding the effect of disturbance and the effect of the process on the control variable. Now, in order to find the transfer function between the set point and the control variable, we're going to assume that the disturbances are zero. And this is the natural way of finding this transfer function. So let's assume that yd is equal to 0. Now one can write y equal to gp times u and then slowly replace each variable with the corresponding transfer function. For instance, u, which is the output of the controller, can be replaced by gv times pt. gv times pt can again be replaced by gip times p, and so on. By replacing the variables with the corresponding transfer functions, we can show that the expression relating the control variable y and the set point is as follows. Now this expression, after collecting terms involving y on the left-hand side, can be written as a transfer function of the form shown here. This is the closed-loop transfer function between the set point and the control variable y. Now this transfer function is obtained by multiplying various other transfer functions in the closed-loop system. Now let's try to find the closed-loop transfer function between the disturbance variable d and the control variable. Just like in the previous case, because we are considering a transfer function between the disturbances and the control variable, we're going to assume that set point changes are 0. Now because the set point changes are 0, we can simplify the related expressions, write y as yd plus yu, and replace yd with gd times u. Go through the standard approach of replacing variables with the corresponding transfer functions. Eventually we can substitute ysp equal to 0 and then collect all the terms involving y on the left-hand side, rearrange various terms, resulting in the final transfer function between the control variable and the disturbance variable. This is the closed-loop transfer function between the disturbance variable and the control variable. It's important to notice that the denominator polynomial for both the closed loop transfer functions we have derived is in fact the same. And this denominator polynomial transfer function is obtained by finding the product of all the transfer functions in the feedback loop and adding 1 to it. And the numerator transfer function is the product of all transfer functions in the path between the disturbance and the control variable, or the set point and the control variable. And this denominator therefore plays a significant role in determining the stability of closed loop transfer functions. It is often written as 1 plus GOL, where OL stands for the loop transfer function, or open loop transfer function, and the open loop transfer function is simply the product of all transfer functions in the feedback loop. Now we might wonder what happens when there is a simultaneous change in the set point and the disturbance variables. In deriving the closed loop transfer functions, we have so far assumed that the input other than the one we are interested in is equal to 0. But what happens if both the disturbances and the set points are changed simultaneously? Because of the elegant superposition principle that works on linear systems, we can simply add the transfer functions corresponding to the disturbances and the set points as shown here. In other words, the response to simultaneous disturbance and set point changes is merely the sum of their individual responses. Now it might appear that this derivation of closed loop transfer functions is rather laborious, but the good news is that there is a very simple thumb rule that one can use in order to derive closed loop transfer functions for any given set of blocks. And they can be written, the closed loop transfer function in general can be written in the following form: Z over ZF equal to pi f over 1 plus pi c, where Z is the output variable of interest or any other internal variable within the feedback loop. ZF is an input variable. For instance, it could be the set point, it could be the disturbance variable. Pi f is the product of all transfer functions in the forward loop, in the loop between the input ZF and the output variable Z. And pi c is the product of every transfer function in the feedback loop. So for the feedback loop, the negative feedback loop that we have considered so far, for set point versus control variable, Z is equal to Y, which is the control variable. The Z in dV versus CV is also Y. ZF for the set point case is the set point itself, and ZF for the disturbance transfer function is the disturbance itself. Now pi f in both cases are the products of transfer functions in the path between the set point and control variable, or disturbance variable and the control variable. Pi c, as it turns out, is the same for both cases because it is simply the product of all transfer functions in the closed loop. Now using the formula here, it's very easy to derive both the transfer functions. Let's look at a simple example where I'm going to illustrate how a given closed loop block diagram can be simplified using the formulas illustrated previously. Now this is an interesting feedback loop. It has two feedback loops, one inside the other. This is what is typically referred to as a cascade loop. In addition to that, it has two disturbances, D1 and D2. What we're going to do is find the closed loop transfer function of the internal feedback loop and then find the closed loop transfer function of the external feedback loop. Now let's call the internal feedback loop G4 and apply the above general rule. That simplifies G4 to GC2 times G1 over 1 plus GC2 times G1 times GM2. Okay, now here is the simplified block diagram. We have replaced the internal feedback loop with G4, the new transfer function of the internal feedback loop. Now we have a feedback loop that is very similar to what we had seen earlier. That's very similar to the standard feedback loop. We can therefore reduce this further, applying the same general rule. G5 is obtained using the rule above, which is the numerator of G5 consists of product of all transfer functions in the path between the set point and the control variable, and the denominator is 1 plus loop transfer function. Now let's start with stability of a closed-loop control system. What do we mean by stability of a closed-loop control system? Let us consider, to illustrate the concept of stability in closed-loop systems, let us consider a simple feedback control system with the following transfer functions. The controller is a proportional controller Kc. The valve Gv is 1 over 2s plus 1. The process transfer function and the disturbance both have the same transfer function, 1 over 5s plus 1. The sensor transfer function is 1 over s plus 1, and the IP transducer transfer function is 1. We would like to show that the closed-loop system produces unstable responses if the controller gain is increased arbitrarily. It is very easy to find the closed-loop transfer function of this system, feedback control system, using the logic we have used earlier. Now we can of course substitute the values of these individual transfer functions and derive a closed-loop transfer function of the form shown here. Clearly, this transfer function, when there is a step change in the set point, is going to be either stable or unstable, but its stability is going to depend on the value of Kc. The stability of any transfer function, including this closed-loop transfer function, depends on the poles of the denominator polynomial. Now, the denominator polynomial is a function of the controller gain Kc, and therefore varying or changing Kc must have an impact on the stability of the closed-loop system. Here is a plot of the output y for a step change in the set point for different values of Kc. When Kc is equal to 2, you will notice that there are mild oscillations and the output or the control variable settles in the neighborhood of the final set point. As Kc is increased to 6, you will notice larger oscillations, but the process still settles in the neighborhood of the new set point. On the other hand, when Kc is equal to 15, the oscillations increase with time and the process eventually becomes unstable. In other words, as you increase the controller gain, the poles of the denominator polynomial appear to be moving towards the imaginary axis and eventually into the right half plane. This is a behavior that is not unique to this particular set of transfer functions we have used in this example, but rather this is a behavior that is characteristic of linear transfer functions and a proportional controller. As you increase the proportional gain, the closed-loop system is likely to become unstable. Now clearly, any good controller, any satisfactory feedback control system must at least be stable. Even if it does not provide the performance that one requires, it has to be at least stable. And that's why we are interested in knowing the values of Kc, tau I, and tau d that ensure that the closed-loop system is in fact stable. Now let's define a general stability criterion. An unconstrained linear system is said to be stable if the output response is bounded for all bounded inputs. Otherwise, it is said to be, the closed-loop system is said to be unstable. Therefore, a closed-loop transfer function is stable if and only if all its poles lie in the left half plane. Now, given that the poles of a closed-loop transfer functions play an important role in determining the stability of the closed-loop system, we have a name for the polynomial equation that is defined by the denominator polynomial of a closed-loop transfer function. It's called the characteristic equation. The characteristic equation is 1 plus GOL equal to 0. And the equation 1 plus GOL has a special name. It's called the characteristic equation. There are different ways using which one can find whether the roots of this characteristic equation are stable or not. One method is called root locus method, where you change the values of Kc, tau I, and tau d and plot the roots or their path. The other method is route stability criterion, which also lets you determine if a given polynomial has any roots in the right half plane or not. It states that a polynomial of the form, an nth order polynomial of the form shown here, will have a right half plane pole if the signs, positive or negative, of the coefficients are not all the same. It also states that if at least one coefficient is 0, then it will have a right half plane pole. If all the coefficients are not negative, then you will have a right half plane pole. Or if at least one coefficient is 0, then you'll have a right half plane pole. If these two conditions are not met, then you'll have to go through a set of steps in order to determine if the polynomial has right half plane poles or not. Now, in the past, when there were no computers, it was essential for students to learn how to do this manually, how to find the roots manually, or at least how to determine if there are roots in the right half plane using those polynomials and a manual algorithm. But given that we have very powerful computers, I think it is no longer needed to learn that approach. Instead, you can use MATLAB to find the roots of a given polynomial.